so that we can build bigger, more complex, larger systems as humans. As humans, we only have limited capacity to understand systems and detail. So the more we can raise the level of thinking, the more complex systems we can build. So we have things that you're probably familiar with, like programming in the large, information hiding, abstract data types, objects, packages, and so on. So software architecture appears first as a discipline in the 1990s, when people began to realize that programming language concepts were not quite enough to understand systems. That you needed other kinds of abstractions, other ways of thinking about systems. It was not just a question of taking a piece of code and putting a little boundary around it. So I'll say more about that in a few minutes. Once architecture became understood a bit, and many things have built on top of it. So the field doesn't stop, because today we have many things that require architecture concepts in order to build the systems we have today. So things like service-oriented architecture, component-based systems, computing, and so on, all are building on the concepts of software architecture. So if we go back and look at the architecture ideas, many of them, and most of them, in fact, have been there for a very long time, almost from the beginning of computing. And the idea was that as we build systems, we need to understand how the pieces fit together. What are the pieces and how do they work together? What you might call structure. Structure, the way the system is organized. So systems have always had structure, and some systems have had very well-defined structure and very well-understood decomposition. Two examples are things like compilers, which have been invented, of course, to compile code, but normally their architecture is built as a sequence of transformations of some source code into executable. Operating systems have also had a lot of attention given to their structure. So here's a compiler example. You can see it follows a sort of standard pipeline architecture. And at that time, when compilers were there, people accepted if you're going to build a compiler, you build it in a certain way. There's a certain style of organization that you need. This is an example of an early operating system developed at MIT called Multics. It was the precursor to the earlier version of Unix that we know well today. At that time, this was the kind of diagram I put in it. It looks very complicated, but in fact, it's actually organized in a very principled way as a sequence of layers in which there are different abstractions that are provided in each layer to the levels above. And so there's a lot of thinking about how do we build operating systems in a principled way, in a clear way that allows us to maintain them and to understand what they're doing. So in the 1970s, there was a lot of interest in how do we talk about structure, particularly code structure. And there's a famous paper by Reamer and Cron who talked about the concept programming in the large. The idea was that when you have many people working on a large system, you have to decompose it into pieces that will be developed by different groups. But you need some way to talk about how they go together. And they were the first to propose new languages for composition. It said, if you want to talk about the structure of a system, well, you need to be able to talk about the parts of the system and the way that they depend on each other. In the 1980s, we see a lot of, maybe we could turn down the volume here, so not so much feedback. Thank you. In the 1980s, when you would read a paper about a system, often you would see a diagram that explains the system. They might look like this, or this. These sorts of pictures here are informal descriptions of how a system is built. And typically they involve sort of graphical boxes and lines often that depict what are the major parts of the system. And the lines often represent the interactions. So here's one that shows that kind of thing. But in the 1980s, there was no general principles behind this kind of thing. Everyone drew their own diagrams. Everyone used different graphical conventions. There were no good guidance or advice for what's a good architecture, what's a bad architecture. And there was very little common understanding about if I'm going to build a system like this, what's an architecture that I should consider. So that's where Mary Shaw and I came in, and we started to identify common patterns of architecture, which we call architecture styles. And this is a way to say there are many standard ways of building systems. Let's give them names, and let's understand when they're useful and when they're not useful. Now that opened up a very large field, and many people have been working in that area. And today, we're in a situation where a lot of things exist to help do architecture, to teach architecture. So here's a short list of things. We have training and certification courses in architecture for industry. We have many standard architectures for certain domains. So if you go to build a system, let's say in the enterprise world, you'll probably use one of a few architectures that are standard. We have life cycle models and process models for how to use architecture in connection with all the other activities we do. We have good ways to evaluate architectures. So someone says, here's my architecture. Is it good? We have techniques now to do that. We also have good ways to document architectures, to communicate them to other people. We have lots of reusable frameworks and platforms that help support certain kinds of architecture. We have career tracks and professional societies, so many companies have a specific job title of software architect. In fact, it was kind of interesting, as an aside, when Bill Gates at Microsoft stepped down from being the CEO, he decided he would still be connected with the company, but he didn't want to be the leader of the company. And so he wanted to pick a title. Bill Gates, what's his title? So does anyone know what he chose as his title? He chose the title Chief Software Architect. So that's what he thought would be cool. So companies have recognized that this is an important role, even if they don't always agree on exactly what that means. But you'll find companies like LG in Korea, for example. If you want to be an architect at that company, you have to go through a rigorous training process to get that job title of education and working with other architects in the company. So they recognize that if you want to be an architect, you can't just put that on your title or your business card. You actually have to learn something, and you have to be able to do architecture. So that's a good example there, but other companies as well have this idea that architects are not just programmers. In fact, they require a different set of skills, and they don't come just easily. You have to actually teach those things, and you have to learn how to be an architect. So in this respect, you would say architecture is very mature. You know, it's reached a level of understanding and acceptance that makes it like any other established subfield of software engineering. For example, requirements analysis or testing. That doesn't mean we know everything about it, but it means at least it's a formalized part of the discipline. So that's a little about the history, but the history doesn't actually tell you necessarily what's important about architecture. When you go to take a course in architecture, what should you learn? If you want to know whether someone's a good architect, what kinds of skills should they have, and what kind of perspective do they bring to a problem? Okay, so there's no single answer to that, but I have my own opinion about the important parts of architecture based on my teaching and working with companies. So the first question is, why do we need architecture at all? Why can't we just all be programmers? Is there any reason to have people spending time doing architecture, or instead, should we just forget about it and allow people to program? So I think there's a big picture answer to this question. If you step back and you say, well, what is the fundamental problem of software development? It's that we have requirements. We may not fully understand them, but we have some requirements. And ultimately, we want to have an implementation of a system that will satisfy those requirements. And that's the big problem we all face. And the question for software engineering is, how do we do this in a way that's effective, cost-effective, that the product we produce is understood and we can trust it, and that we know how to manage the resources to do that. So that's the big challenge for software engineering. Now, for many development, unfortunately, what people do is they just build the system and they pray that it will work. They do a lot of testing, and they hope if they test it enough, if they find a problem, they go back and fix it. And so there's a cycle, often very costly cycle of development, because you may make mistakes along the way. You only discover those at the very end when you're doing testing. And they can be very expensive to fix, or impossible in some cases. So what architecture says, instead, let's decompose the problem into two parts. Let's think about high-level design of the system, what we call architecture design, that will allow us to think about the most important requirements of the system. And not just the function of the system, but also the non-functional aspects, the quality attributes that we care about, such as performance and scalability. And then, once we've made good decisions at a very top level, we can then proceed to actually build the implementation. And the fact that we've broken it into two parts actually simplifies the problem. We have more confidence that what we build at the end will satisfy the requirements because we've already done a lot of work at the middle level. And that work is work that can be easily changed. If we discover, for example, when we're doing architecture design, that their performance will not be good enough for security, we can make those changes very cheaply. But not so in the implementation. It also allows us to do a different kind of reuse. So architecture reuse is not like code reuse. Code reuse, of course, you need libraries, you need management of the code artifacts. Architecture reuse is more about common ideas, common ways of thinking about the system. And so it's not quite the same thing, but it's a very powerful technique because it means if you're an architect, you don't have to start from scratch. You don't have to start with a blank piece of paper. You can start with architecture designs that already exist, and then you can use those to build your system. So when I talk about making important decisions, I think that may not be completely clear. So I want to give you an example of this idea and how architecture can help. So here's a architecture of a well-known system, Google. This is a diagram that was published by Google developers a long time ago, in the early days, that described how they designed their back end, the document management portion of their search engines. And the idea was to explain the rationale, the reasons for organizing the system the way they did. Let me walk you through one way to think about this and try to relate that to architecture. So the first thing you'll note about this diagram here is it's at a very high level. It doesn't show you any code, it doesn't show you APIs, it shows you major pieces and lines that show you what's communicated. So when we think about doing a good architecture, the starting point is to say, what do we mean by good? What are the requirements for the system? Now, the functional properties of the system are, in fact, incredibly simple. For the Google backend, you need to be able to store, update, and retrieve documents. What could be simpler? Put a document in, I can change it, I can get it out. Anyone could write a program to do that. So why is it a difficult problem for Google? Well, when you think about it, it's difficult for a number of reasons. There are qualities that are important beyond the function. The qualities are things like scalability. How do I manage 1 billion users? Reliability. System can't go down. Performance. If I request a document, it better not take 2 minutes to get the document back. And from a business perspective, cost is important. We're going to have a lot of infrastructure. We want to reduce operating costs of that. So these are the qualities that make the system interesting and challenging for an architect. It's not what it does. It's how it does it. And the question is, how do we build a system that satisfies properties like that, what we call quality attributes? So I can give you my interpretation of why this is a good architecture for those qualities. The first is, if we think about scalability, we're going to have to store a lot of information, and so we need a way to expand that indefinitely. And so Google decided to use what's standard now as a kind of horizontal scalability. where if you need to store more information, you buy more disks, and you buy more servers, and you put them in a big data warehouse, and so you can keep adding resources. Okay, so that's fairly straightforward. I think most people would think of that. The next question is, what kind of storage, what kind of servers should you use? And for that, you have to consider alternatives, such as, on the one hand, we might purchase very reliable and high-performance servers and disks, RAID servers and so on, or we might go the other way. We might pick very cheap, off-the-shelf hardware and server technology. Do you know what Google picked? Cheap or expensive? Cheap. So they said, we're going to use only very, very simple disks and very simple servers, and that will keep the costs down, both in terms of hardware and software. So that was a business decision and a technical decision. The problem now is we have a new challenge. Having made that decision, we now have the problem that those are going to crash and fail. We'll have a lot of failures in our infrastructure because that's the way it works. So the question is now, how do we go back, get reliability back into the system now that we've handled scalability and cost? And this is where the story gets interesting, because this component here, which is called the Google File System Master, is a component that's responsible for making sure that the system continues to run effectively. And what it does is it monitors all of the servers and disks, and when something isn't working, it takes it out automatically and redistributes the load of the information across the remaining servers that it has there. So it's continuously repairing itself. It's continuously monitoring and fixing itself as it runs. So that's a new idea. It was new at the time anyway, and a very interesting architectural choice for building the system. But we're not done, because the way the system was designed is to retrieve a document, you must go to the master and find out where it is, and then get it. That means that the master will be a bottleneck, a performance bottleneck, meaning if everything goes through the master, then the whole system won't scale to large numbers and have good performance. So for that, we now need to do some very careful design of the connectors, of the protocols of interaction, to make sure we don't overload the master. And so the protocol there has a very lightweight protocol for finding a document, but all of the heavy data transfer goes point to point between the consumer and the back end. So what's the point here? The point is that architecture design is not so much about functionality. Of course, it's important, but the hard problems are dealing with the quality attributes of the system. And the thing that makes it difficult is we can't have everything. When we make a decision to improve one quality, we often affect another quality that requires us to balance out those choices and to make decisions that are mutually dependent. And this is why it's difficult to do architecture, because it's very complex to understand those trade-offs and how we can meet or maximize all of them. The other thing that's very important about architecture is that it's not just what goes on in the boxes. It's also very important to know what goes on in the lines, because the lines, how things communicate, will have a big impact on things like security and performance and reliability. So this is an example of what I mean by sort of architecture thinking. It's being able to think at this high level in terms of the qualities of the system and the kinds of system structure that will achieve the qualities we want. So the next key idea here is the idea of architecture reuse. I mentioned that earlier, but I'd like to clarify that a bit. I know there's a lot of work here in product lines, and I want to relate that to architecture. So when we think about reuse, we can think about it as being often a trade-off between the generality of the thing we're using and the amount of benefit we get from reuse. I have it called power and specialization. What I mean by that is that if we have something very general, not specialized, it will be very usable in many areas, but it won't give us a lot of benefit. So if we think about the simplest notion of architecture patterns, we can think about things like call return or events or data flow as a very general notion of how a system computes and communicates among the parts. And those are very, very general ideas. They help to understand how the system works, but they don't give you reuse of code, they don't give you analytics, they don't give you anything else. If we make it more specialized, we can begin to provide real support. So a good example would be the idea of pipes and filters that Unix promoted. So it's a kind of data flow architecture style, but it comes with additional constraints and with a body of code and operating system support. So that if you want to use that style of coordination, it's actually very easy. So it's more specialized. It doesn't give you as much generality, but it gives you more power. We can look at other more specialized areas of component integration platforms. So these are, you can think of it as frameworks for communication or distributed systems. And there are many of those out there. Then we get things that are even more domain specific, which really work only within a certain class of hardware and applications, until we finally get over here to product lines, which are specialized to a particular company and a particular kind of product within that company. So as we move from the left to the right, we have more specialization, more features in that reuse that we can take advantage of, and we can build tools and code generators as we move to the right here. So when you think about reuse in architecture, you have to figure out where you want to be. And it's not always clear. If you take the example of Android versus Apple operating system, iOS, there are different points on the spectrum here. I put iPhone there, but if you think about Android, it's to the left here. Android is more open, it's more general, it allows you to do more things, but it also makes it possible to do bad things, or to make bugs, have bugs you can't do in Apple. So in the Apple world, you have more constraints. You probably can't run iOS on an arbitrary device, but you can run Android on an arbitrary device. So you have more generality with Android, but fewer guidance and constraints that make it easier to use, but more potentially buggy. So that's a good example of where two different companies or industries have made a different choice where they want to be on that curve. And again, when you think about, if you think about developing systems or building something like one of these things, you have to decide how general is my system. So this is very related to a topic we were talking about on this was Monday of product line scoping. And how general should the product line be? Is it a very focused, small piece of reuse, or is it a very general piece of reuse that applies retroactively? Another thing that's important, I think, is this idea of architecture style, or organizations of systems adapt over time. They change, but they don't ever go away. I want to give you an example today from the data flow world, because I think it illustrates a general evolution pattern for architecture. So a data flow system, in the very most general sense, is a system that takes data in, transforms it, and produces some output. The transformation is usually done by a sequence of components, each of which performs some portion of that, maybe in parallel or maybe not, in order to achieve the end-to-end transformation that you want. So in the early days of computing, we had this. So we had, when I say early days, I mean mainframes. We had mainframes and very limited computational and data storage. We couldn't actually put a whole program inside the computer. We had to break it apart into steps. And so we would read in some data, we would transform it, we'd write it back out using some physical medium like tape. We'd read it back in and then transform it. So it was a sequence of steps here to achieve some end-to-end analysis. So that's very old technology, but was one of the first architecture styles to be invented. Later on, we began to get the idea of concurrent processing. So instead of each step completing, we could have data flowing through. And we see this today in many systems where you have sensors, data streams coming in, and you need to process that sensor stream in a variety of ways. And so this became something called pipes and filters. Again, Unix also had this idea. But this is now, it takes advantage of the fact that computing technology is cheaper, so we can parallelize and pipeline the computation. More recently, here's the Apache web server. If you look inside the web server, you discover that on the input processing, you essentially have a pipeline of transformations. And on the output side also. And you can go in and actually change that. You can add your own components in the middle of that processing if you want to do some special purpose processing on either input or output. For many years, there was a very interesting extension of this idea to the World Wide Web, in which you could create your own data flow environments graphically on Yahoo, and all of the components are reusable transformation components that run on their servers and work at the scale of the internet with very large amounts of data. So you can process data streams and have interesting results. So here's a pipe. Oops. This is an architecture design for a system that looks for apartments near someplace. So if you wanted to find an apartment near Carnegie Mellon, let's say you're a student and you're moving there to study, you might want to find a cheap apartment. This will process various news feeds to find the apartments and then show you the result on a map. And the interesting thing about this is now everyone can do this. And you can just sit down with any laptop and use Yahoo Pipes now to do this kind of processing. Although, unfortunately, this effort discontinued, and so they no longer support that. Another more recent form of this is MapReduce. So if you think about Google's framework and others for taking large amounts of data and processing, that's essentially a kind of pipe filter architecture, but it's very structured in terms of map and reduce operations. So the point here is that as we move through time, technology changes. We have different costs and resources that we can get for those costs, which change the way that we deploy this idea. But the idea stays the same. The concept of taking input data, transforming it step by step to get the outputs, same idea, same philosophy, same concept, just different way in which it's realized. Now, you can see, if you look at any of the other styles, standard architecture styles, you'll see same thing. You have old ways of doing it and new ways of doing it, but the concepts remain the same. Now, why is that important? That's important because it means if you're an architect, you need to learn these things because they're not going to go away. It's not that suddenly tomorrow there'll be a whole new ways of building systems. Yes, the details will be different, but the fundamental architecture concepts will be there. Another idea here that I'm extremely passionate about is the idea that when we draw architectures, we often have boxes and lines, right? And the boxes usually represent some computation or some data storage. But what do the lines mean? What do the lines mean? Well, for many people, they don't know what the lines mean. They mean there's some kind of interaction going on there. Maybe data is flowing, maybe there are asynchronous events, maybe it's a pipeline, whatever. So today, architecture, I think if you're going to be an architect or study it, it's extremely important to focus on the connectors. What do they mean? Because the actual overall composition depends a huge amount on what those connectors are doing. Unfortunately, it's often ignored. So to me, this is one of the areas which unfortunately is not as well practiced as other aspects of architecture. But I wanted to illustrate why it's important and why informal concepts are not sufficient. So imagine I have two components. We'll assume they're data flow components. So we have two what we'll call filters, and there's a pipeline or a pipe between them. The purpose of the pipe is to buffer data so that the two components can work concurrently and somewhat asynchronously. Okay, so we might understand that at that intuitive level, I've just given you a description, but if we actually wanted to use this or analyze it, we need to know more. Well, first of all, we need to know which is reading and which is writing. Okay, so there's a little bit of semantics there that's not clear from this diagram. But here are some questions that are not so easy to answer. What happens to F2 if it tries to read and there's no data? Does it block or does it continue? Either choice might be okay, but you need to know that. Can F1 stop writing? And if so, how do we know it's done? Can F2 stop reading and say, I'm done, even if there's data still coming down the pipe? Is that okay? If F1 can stop writing and closes its end of the pipe, Could it start up again later? Could it change its mind and say, oh wait, we've got more data for you? What happens if F2 is really lazy and never reads, and F1 keeps providing data? What happens? Does F1 block? Do you throw away data? So all of those are interesting questions about the interaction that we can't answer when we just see a line. We need to go down underneath it to understand the properties of that interaction. And without that, we can't build F1 and F2. And we probably can't reason about performance. We don't know if components are going to block or not. Okay, so my point here is that connectors are one of the most important things for the field of architecture. And the reason why it's new relative to programming is that when we program, we have a very limited set of connectors. We have procedure call and data reads. That's it. That's what the programming language gives us. So we don't need to spend a lot of time understanding those, because every programming language has those. But when you go to architecture, now we have these very interesting, rich semantics of communication and interaction that now require much, much more attention to what they do. A good example here is when I worked with the Department of Defense to create a standard for imposing simulations on a bus. They wanted to put together simulations, let's say, for example, for NATO, to simulate some kind of military scenario. And the question was, how do you come up with a standard that all of the simulators can use? And essentially, it was a problem of defining the bus there. What's the protocol of the bus? What can you do as a simulation? So this was a really, really heavy, big connector that required a lot of specification, which we actually helped them do. The last idea that I want to talk about is the idea of, well, what do you say when you want to describe an architecture? For many years, there were huge debates about that. People would say, on the one hand, tell me what your code looks like. And other people say, no, that's not important. I want to know, how do you deploy it on physical systems? Where are the networks? Where are the computers? And other people would say, no, what I care about are the protocols of interaction. And so there were a lot of people who said, I think architecture is this, and someone else said, no, I think architecture is this. And no one was making much progress because they were spending too much time arguing about what architecture should be. And finally, everyone got smart and they said, well, look, there are many kinds of things you want to talk about when you describe an architecture. And let's not try to put them all in one place. Let's have the idea of multiple views of the architecture, where each view describes some area of concern. And so today, we have a general notion that when you describe architecture, you usually must provide multiple descriptions to represent different kinds of design issues. So if you're worried about maintainability, you probably need to know the structure of the code. So that if I change a piece of the code, I know what it affects. But if I'm worried about performance, I probably want a view of the runtime system so that I can understand how that works. The book we wrote on documenting software architecture, Views and Beyond, is really this philosophy here. It says, if you want to write down an architecture, you need to do it with multiple views. Okay, so now I want to look at what's next. So I've been talking about the history of architecture. I talked about what I think are some of the important ideas that make it different than other things in software engineering. And now I want to talk about some of the emerging areas that people are looking at. make it fairly quick because you've been very patient with me up until now. But we can talk more about this later. These are actually connected to my own research. There are many other research efforts in architecture that I won't talk about. But one is, how do you build the right tools for architects? Second one, how do you deal with cyber-physical systems, or if you like, IoT, Internet of Things? And finally, how do we make our systems really robust today so that they can survive in the face of faults, attacks, changing environments, and so on? So, architecture tools are today still not very good. Most people, when they do architecture, use PowerPoint or some other graphical tool, which is okay, but it doesn't actually give you any formal basis for analysis. So what we would like to have are tools that are often probably domain specific, but allow the architect to really check the architectures to make sure they have certain properties. This is our tools here, which are available for free. You can download them. It's called Acme Studio, and it allows you to define architecture styles and do analysis of them. So this is an architecture style for automotive systems, and it analyzes real-time schedulability. By the way, we can make these slides available, right? Can we make these slides available to people in this room later? We can post them. I know people are taking pictures here. But it'd be more efficient if you listen and we make it available. Is that okay? Can we do that later? Okay. So you're not, for this tool, you can analyze schedulability and do various kinds of things like discover whether certain kinds of deadlines will be missed under certain, in certain contexts. In another world of health management systems, you can discover whether your servers will be overloaded using theory. Okay, so tools is the first area. A second area is cyber-physical systems. If you study cyber-physical systems, something you realize very quickly is it's not all software, obviously, but what that means is that when you try to think about when you try to think about designing your system, you need to worry about more than just what the software does. You have to understand what the physical system is doing as well, and you have to integrate those. In fact, it's more than just that. So if you think about designing a drone of some sort, you probably have a design for the control of the propellers. You probably have a model of the physical device, and you probably have some idea about the hardware. What is its capability, its cycle, its timing, and its connectivity here. And you probably have some models of the software, for example, that allow the ground system to talk to the drone securely. Okay, so each of those different models represents a different kind of concern and requires different expertise. So people who do control systems may not understand the software here very well, or may not be able to do the hardware design, or physical design. So the problem becomes now, when you do architecture, it's not just software. You have to think about bringing together different designs from different organizations, different people, different tools, different kinds of analyses. So how do you do that? How do you manage to bring everything together. Well, here's one idea that we're looking at, and that is, assuming you have these different models for different areas, let's say control and hardware, we map those to an architecture view. So it says, essentially, ignore the low-level details, but tell me at a high level what this model does. And then we integrate those to create a larger architecture that has both physical and software things in it. So essentially, we use the architecture as the integration mechanism for these low-level models that form a cyber-physical system. So architecture plays a central role in becoming the place where everyone can say, what is my design to do in terms of the overall system? Resilient architectures. There's a lot of interest over the past 2 decades on systems that are more capable of fixing themselves. Today, systems are actually very brittle. They break easily. You might think we've done a very good job in terms of making systems that are highly available, and we have, but still, there are all kinds of problems that we run into because the systems are not smart enough to fix themselves. When a problem occurs, often a human must get involved to fix it. And so we would like to build systems that take control over their own health, that improve themselves if they see that things are not working well. The general idea that most people are following here when they think about solving this problem is to go from open loop to closed loop systems. What I mean by that is, if we have an executing system, or whatever, today we deploy that system and we may monitor it with a human, but the idea is to have a control layer that automatically senses what the state of the system is and the environment, and then looks to see if there's a problem and whether it can fix it, and then changes the system. So we architecturally decompose every system into the base system that does the primary functions, and then a control system that's looking over the shoulder of that system and attempting to see problems and fix them at runtime. It's the kind of thing we do at design time. You know, if you put a product out and there's a problem with it, in the old days, we go back, we would fix the problem and we would redeploy that, or put it out again. We still do that, but the idea is to do that at runtime while the system is operating, is to have the system fix itself. This has many names, by the way. Sometimes it's called self-healing systems, sometimes autonomic computing, sometimes self-adaptive systems, sometimes autonomous systems even. And so all of these systems have the idea that they have more intelligence about themselves. This control mechanism says the system knows how well it's working itself. It knows how well it's working, and it knows how to fix itself. So it takes responsibility for improving its behavior. So we built a framework, a reusable continuous product line that does that. It makes it easy for someone now to take a system that they have already and add this control layer to it. So we don't have time to go into details, but this is the big picture here. We have our system, we have to monitor it, we update models at runtime, and then we have an adaptation manager that looks to see at those runtime models whether the system satisfies its requirements at that time. And if not, it fixes it. In more detail, it looks like this. And I'm not going to have time to go over that. So I'm going to skip over this here. Building on this idea of resilient architectures, there are many, many interesting research topics. And one of my other talks is really about this, which I won't be able to do on this trip, but maybe another trip. Security is a really difficult problem to deal with. How does a system know when it's under attack and fix that? The motivation for much of this work was to get humans out of the loop, to not have people looking at the machine and the system to fix it, but have the system do it itself. But in reality, we need systems with both humans and systems working together. And so the question is, how do we get the coordination we want? This is very closely related to the whole problem of AI and trust. You know, AI in systems, artificial intelligence in systems, puts more intelligence into the system and more autonomy. So the system does more, but how do we trust it? How do we know it's doing the right thing? And how do we get it to learn to do the right thing from the humans that are using the system or appearing? So this is a very important area here. Applying this idea to smart environments and IoT environments to make systems that are good for the humans in the environment, I think are very important. One of the problems that you run into when you do this kind of work is that when you're trying to decide what to do to fix a problem, there's a huge space of alternatives. There are many things you could do, and deciding what's the best is computationally very hard. You can imagine it as a search problem of how do I search for all possible plans to make the system better. So we need to find efficient ways to do that. And one of the things we're looking at now is using genetic algorithms to discover new strategies or plans to improve the system. And finally, one of the things that challenges our normal thinking about design is that when you work in this area, there's a lot of uncertainty. You don't know exactly what your system is doing. You don't know exactly what the environment is doing. You may not know if some client is running a denial of service attack or just needs a lot of data at the moment. There are many, many uncertainties in making this kind of thing work. And so you can't ignore those. You cannot ignore those uncertainties. You have to find a way to get the job done, even with those uncertainties. What that means from a formal point of view is that models almost necessarily become probabilistic models. The kinds of models that you're looking at, you say, well, if I make this change to the system, what's the outcome? Well, you don't know exactly what the outcome is. It's going to be a probability distribution over final states. And so, so it makes the complexity of models and tools much harder. That's the bad thing. The good thing is, in fact, there are a lot of new developments in terms of probabilistic modeling tools and model checkers and things like stochastic probabilistic games that we can build on top of. So we're not alone in working on this, but I think it's an important dimension to that area of bringing uncertainty. Okay, so let me conclude here. Architecture evolved from the 1980s, where it was informal, to where we are in the 90s, and today we have a lot of resources for the architect. That architecture thinking, my favorite phrase there is, helps put the engineering in software engineering. What I mean by that is, what is engineering? Well, engineering is making trade-offs, good design trade-offs, and this is where architecture is a very useful tool. We looked at some of the components of architecture thinking, like focus on connectors, understand the kind of reuse, and so And so there's important ideas in architecture thinking. And for the future, well, there are a lot of really great research problems and challenges that we're facing as we move architecture into the new world. I will stop there, and thank you very much for your attention.
Oh, thank you very much. Now, someone has one question.
Okay. Thank you, David, for the presentation, your good presentation. As a member of the PhD program in electronic science, I would like to say thank you for being here. We know that your agenda is fully, but the opportunity to have with us is very, very helpful for us. We are working on aspects about human-computer interaction and software engineering. About that, I would like to ask you something that is we have been thinking some weeks ago, and it's about ethics and values. I mean, there is an approach called value-sensitive design. I don't know if you have been heard about this new approach. What is your impression? What did you think about how to integrate these human values in this aspect of software architecture? Because we produce technology for the people, but if we don't introduce these concepts in the software, what could be the future?
So I think there are two sides to this. One is looking inside the architecture and saying, if we think of ethical computing as a quality, we can imagine trying to build it in as part of our design thinking when we do the architecture. But I think the more important side of that is an aspect of architecture that's often not appreciated, and that is good architectures must work within an ecosystem, within a context. So it's not just the system itself, it's everything else around it, which includes policy, it includes understandings and cultures and things like that. And I didn't talk about that. There's some work I'm doing with some people at Carnegie Mellon of trying to understand socio-technical ecosystems. And so the architecture is a part of an ecosystem. It enables certain kinds of activities to go on, but only in the context of many other things. So if you think, for example, of social networks, for instance, okay, well, there's obviously a lot of technology there that we can think about their architecture. The question is, though, how does that interact with the way, what sort of ethical norms should be built into it in order to represent the ecosystem? And I think it's a very interesting combination that we need of social science, maybe psychology, and systems that have to come together. So I would agree with you; it's extremely important, but it's going to definitely be a multidisciplinary kind of effort.
Any other questions?
Speak louder. Yeah, some notes here. So, thank you very much for a very comprehensive lecture on software architectures. I'm curious about something you mentioned when you mentioned standard architectures for different domains. I'm quite familiar with the domain of healthcare, which is very, very complex. And from that perspective, if we have a broader approach, more in the domain of enterprise architecture, for instance, that has been maybe the work performed around that. There is a big problem in this domain because when we think about the complexity of these systems, normally the work on the standards has been like the approach designing enterprise architectures has been promoted as a solution. But in practice, that has been very difficult. In the US, it's difficult. much more complex because many reasons. So the question is, from the perspective of enterprise architectures, what will like the way to go when there are many requirements to be met, and we have this complex problem? Because here we were talking about more software architecture, but if you think about enterprise architecture.
Well, here again, I think there's a sort of a technology side, and then there's a ecosystem side. And I think again, it's easy from the technology side to come up with a solution that won't work because it doesn't match with the financial incentives or the regulatory requirements and so on. And I think architects are often not sufficiently aware of those concerns when they design their architecture. So for example, they might say, well, let's come up with a standard of electronic health record and protocol for using that. But no company has an incentive to use it. So I think many of these really hard problems of matching architecture to solve a problem require a deep understanding of the ecosystem and the constraints in that. For example, I think an important one in healthcare is, can you actually identify who the person is, right? So in the United States, we don't have an identifier across all systems. So if I have hospital A that wants to communicate with hospital B, how do they know who they're talking about? Now that's not a problem in our military health systems, because everyone in the military has a ID. And so many problems go away for that. But that's an ecosystem problem. That's a question, and partly ethics too. Most people in the United States say, no, you don't want a number. That violates our sense of what our government should do. And so they're not going to allow that to happen. Whereas a technologist might say, well, we just give everyone a number, it'll all be easy. So I think this is interplay. The other thing I'd like to say is I think, more and more, we need to think about organic architectures. What I mean by that is architectures without centralized control. There'll be standards, but there will be many systems of systems, each of which has an architecture. Of course, there has to be rules for them to interact, but we need to allow a certain amount of autonomy in each of these things in order to allow them to flourish in their own way. So I think there's some challenges at the technical side. How do you build good systems of systems? What kinds of protocols do you use? But the bigger challenge really is matching the architecture choices with the ecosystem that's in. And I think, sometimes ecosystems can be impacted too. And you might decide, well, today the regulations cause us to make this architecture, but if we change that, or change the incentive system, from the outside, now a new architecture is possible. So again, I think it's working across the boundaries. It's really critical there, for something at that scale to work.
Just one comment. So that you think about architecture of ecosystems, that could be an area that is, or a recent topic area that is going after enterprise architectures, or how's that in the context of research?
It's a good question. I'll give you an example from my own experience, not healthcare, but in the early days when people were starting to do research in architecture, there were many projects that said, I'm going to create an architecture language and a tool. And there were maybe 25 projects that were being sponsored by the government and industry. And each of these was different. Each of them had benefits and disadvantages. The funders from the government who funded me said, this is crazy. There's no interoperability here. So I can't take this tool that was developed at Stanford and make it work with the tool that was developed at Carnegie Mellon. So they gave me the test to fix this. And so we had a problem because we didn't want to force everyone to use the same thing. At the same time, we wanted interoperability. So what do? We got an agreement on a baseline core set of information that everyone could agree, yes, if you don't have that, you don't have architecture. And then allow people a very open-ended set of additional things that they put in. So we ended up with a compromise in which certain agreements allowed us to standardize some things, but have extensibility. Now, what that also allowed is if I understand your extensions and you understand mine, now we can do something more. So it gave a baseline where everyone could play, but also enabled other agreements to occur. And so I think something like that is the sort of that you need to recognize that there are these differences and support that, but at the same time find some kind of basis for commonality. It's a generic answer, but I think healthcare could learn from that.
I have one question. What about training for new architects for faith in new challenges?
Yeah, that's a really good question. So I've been teaching architecture for 20 years now, and I just realized I've been teaching it wrong all these years. I didn't talk about this as a different talk, but you know, there's a kind of myth, or what I think is a fantasy, and that is that we train these really smart architects, and they come into the company and they figure out all the hard problems. Well, that hasn't really happened. It somewhat has happened, but I think the problem is that when people do development, they make architecture decisions all the time, but they don't have the architecture expertise. We say, oh, no, the architect knows that, but then the programmers don't know it, so there's a mismatch there. I think what we have to do is push architecture down so that everyone is aware of architecture and the role they play. And so that architecture is more of a collaborative effort than a dictated one, more of a democracy of architecture choices. But I don't mean chaos. I don't mean everyone does the same. What I mean is that programmers are educated to know when they're making an architecture decision and have a process for making sure they're making the right ones through a group in an agile process or through talking to an architect or something. So that the idea of architecture thinking is no longer just the architects. It's now pervasive across all developers. So I think we need to start teaching architecture much earlier. And I think we need to be explaining to people, when you make this decision, realize you're making a quality attribute trade-off here. And you better do that right. Okay, so I don't know how to teach that yet, but I think that's what needs to happen. So we have a course in software architecture, and they're for master students, and train them to be architects, and that's good. But I would like to find a way to move that out from there to the masses.
Which things that courses that we do in requirements implement?
No.
For the
Say it once again, we didn't get all of it.
The software requirements, contribution to software side.
Well, that picture I drew with the requirements and the implementation and architecture in the middle, what that means is architecture is a bridge. It's a bridge, and if you have a bridge, you need to understand what's on both sides, which means the architect has to understand the implications on implementation. How are we going to build it? But they also have to really understand the requirements. This actually is, I think, the hardest thing for an architect. And I think when we teach architecture, almost half the course is how do you come up with good architecture requirements? Because if you talk to most people, they say, oh, well, we want high performance, and we want high reliability, and we want everything. I said, yeah, great, go build it. Well, you can't. And so an architect's role in defining requirements has to be to say, well, there are constraints here. you can't have everything, so let's talk about how we're going to make trade-offs. And this is not a skill that requirements engineers always have. They need someone that understands the implementation decisions and how those affect them. So this is architects are really important in the requirements process.
First, thank you for you visiting us here and for your contribution with this kind of event. I would like to know, you mentioned something about client-driven requirements, and maybe that's the problem that startups have all the time. They start developing something, they define an architecture, and it's a question about how much architecture is enough. Particularly, we have a problem in that the client always changes the requirements. And you say, we developed, I don't know, this feature, and we believe that's the clear feature for our application, and we release it to production, but no, the community doesn't say that's not a good feature, and maybe they decide something. How can one approach that kind of context? Like I don't know, the architecture you define is not enough to answer to those changes. Maybe there are patterns. I don't know if you mentioned that the silent systems were one approach to go with that. In your experience, that for startups that works, it's too much work, or maybe.
Right. Well, that's a really good question. There are a lot of debates today about how do you integrate agile practices with architecture, where agile attempts to address the problem of requirements change. As you build a system, you discover you need something that you didn't know about. And so you say, well, if that's happening, then how can we do architecture? So there's a lot of discussion about that, and I think people are now discovering ways to integrate those. And the way I see it is, you can think of architecture as a barrier to change or as an enabler of change. And what I mean by that, if architecture is too constrained, says you can only do this and this, then you may be bad because you can't extend it the way you want. On the other hand, if you say the architecture has a certain set of agreements that we all subscribe to, if you change those, you've got a problem. But on top of that, you have many degrees of flexibility. The problem is you have to have some concept of how the system will evolve. It can't be arbitrary. So the other thing is, I think you need to use architecture not for everything, but for the really important decisions. How do you decide what's important? Well, that's very domain specific. There's a good book I would recommend, maybe you've seen it, called Just Enough Software Architecture. Just Enough Software Architecture. And it's written to practitioners who say, well, look, we're not going to go off and spend 2 months doing architecture. I want to know just how much to use and when. So this was written by a student of mine. His name is Fairbanks. Last name. So I recommend that book. There's another book out very recently by another student of mine called Design It! Exclamation point. Design It. And that's by a guy named Keeling, K-E-E-L-I-N-G. And he works very much with agile groups and tries to get them to do architecture decisions that are part of the process that are being done. So he has some kind of pair architecting where people work together to make architecture decisions, for instance. So I think there are approaches now emerging that find the right balance of this. Yeah, but it's definitely a tough fight.
Yeah. First of all, thank you for the opportunity to listen to all that knowledge you have. But I have a little question about, and it could sound a little bit rocky, unexperienced. But my question is about that, the experience. So there's a gap even more and more and more wide about how to get the real knowledge about solar engineering and how to the architecture becomes a real solution because everybody says that it is only about experience, no? But it even could be more complicated. So my question is how we can get that gap without dealing without experience.
Yeah. Well, I think to be a good architect requires domain knowledge. There's some general principles, but if you're going to design a space system, you have architecture problems that you don't have in an enterprise system, or you don't have on a mobile app. And so when you look at being a good architect, I didn't talk about this, but beyond the overall architecture structures, there are things we call tactics. And a tactic is a smaller decision that you make to improve some quality. I'll give you an example. Suppose you want to improve the reliability of your system, and you may have some failures in some components. What you'd like to do is detect if there's a problem so that you can not crash. Okay, so how do you do that? Well, there are at least three tactics that I think of. One is called a heartbeat. A heartbeat says, okay, the component puts out a message periodically, says, I'm alive, I'm fine. Okay? And so you listen for that. Another one is what's called ping echo. Ping echo says, if I want to know if this component's alive, I say ping, and I get something back. If I don't get it back, then I know it's not working. And the third one is exception. I wait until I need it, and then I get an exception back and say it didn't work. Three different mechanisms, three tactics. Which ones to use? Most people will just pick one because that's what they use before. They don't think about the trade-offs. But once you start studying that, you say, well, there are trade-offs. Heartbeat requires fewer messages than ping echo. Ping echo, however, gives you more flexibility in terms of when you check. Exception is good, very low overhead, except we don't know about the problem until it's too late. So there are these trade-offs in terms of which of those tactics you pick. Okay, so this is an example of a domain-specific knowledge about reliability, which you can learn. Now, it's domain-specific in that it relates to that quality. But, so if you're going to be an architect, you need to know a lot of those. How do I improve availability? How do I improve performance and so on? How you do that will depend a lot on the domain. But, so I think the answer is somewhere in between. You need experience, but it's architecture knowledge that will help you, not just building a lot of systems.
And the last question.
Yes, thank you for coming. And I have a question about design decisions. What is the best way to record the rationale or the reason behind of architectural decisions?
So, yeah, so how do we write down the decisions and make those available? It's a really good question because I think if you do it wrong, you end up with too much documentation and it's very difficult to know what are the important decisions. I think the first thing is to have some process for recording decisions. The book I mentioned called Design It before, they work with a process where each development division has an architecture decision record. So whenever they make an architecture decision, they write it down there with the rationale why they did it. So this is very much sort of as it develops rationale, so when they make the decision. And that's very lightweight. The other one is a much heavier weight, where you say, okay, here's our architecture, here are the design choices we made, here's why we made them. That's what we teach our students to do now. I think the problem with making these decisions, however, is that often it's not adequately related to the requirements. In other words, you make a decision, but you don't say, I'm doing this decision because of this quality. It's the hardest thing to teach. So we teach our students, when they do an architecture design, you need to write down the requirements, or the attributes you need. And then you need to show me your design, architecture. So they do that, The problem is, they're not very good at connecting those two. And that's the hard part, is to make sure that the decisions you make are related back to the requirements of the system. So you can say, this is the right decision, rather than just something I decided. Okay?
And how about the detail of the rationale?
Well, that really depends a lot, I think, the amount of detail that you put on your development organization. You know, the other thing that I think is very important about architecture, again, a myth about that we tend to teach, is that an architect gets to start from a white sheet of paper and write down their favorite architecture. And it almost never happens. Almost never happens, because the reality is of software development is you build on top of frameworks and components and libraries and protocols that you don't design. And that establishes an architecture context or decisions you don't have choice about. So if I use some microservices architecture, chances are many of the architecture decisions are already made. And so the question, so I don't want to spend a lot of time documenting that, because it's not going to change. It's not something I choice about. It's the decisions I make on top of it. So I think we need to be able to, in some sense, reuse a body of decisions by bringing in other frameworks and platforms that have an architecture already in them. Take, writing an app in Android, for example, or iOS. A lot of what you do is prescribed by the framework. You don't have too many choices. But there are choices you have. For example, let's suppose you want to place ads in your app. How do you decide what kind of app libraries to use? That's a choice the app maker is going to develop, which will have impact on things like usability, power consumption, a lot of things. So that's a set of decisions that are outside the framework. But many other ones, like permissions, the security things, those are all specified. So I think we have to make it efficient by documenting decisions that we make, and not the ones that were made for us.
Thank you so much, lady, for coming here in our studios and platform.